Hello everyone and welcome to the CH300 in Advanced Retrosynthesis. This is the fourth video and today we will see heteroatoms, heterocyclic disconnections and other cyclisations. In particular, we will see all the disconnections and synthesis that involve carbon heteroatoms. We will use them for the formation of heterocyclic compounds, and towards the end we will see their uses for other kind of cyclisations. Let's remember that whatever you see in this video is something that is not completely new to you. The heteroatom disconnection is something that you have seen largely before. They belong to the category of the CH disconnections, so it's a very simple but important synthesis and is very useful for the retrosynthesis point of view. We can start from an Rx compound and we want to disconnect, of course, from the typical disconnection approach in cutting the bond here between the R group, that remember it might be a much larger part of a complex molecule, and as a synthon we can have the R with the plus, so here is the electrophilic site, and the X actually should be the nucleophilic part. So as a synthetic equivalence, we can have any compounds with an halogen, which act as a leaving group, or we can have an activated alcohol. We have seen how to activate alcohol in a previous video. Remember that the hydroxyl group itself is not a very good leaving group. So these are the typical compounds that we can use. This one, for instance, is a tosylate, which is a typical activating group of an alcohol, or you can also use a mesylate. That depends on what you want to do in the lab. Let's see a typical example. Let's say that we want to disconnect this molecule. This is a typical carbon-nitrogen bond. So normally when we see this kind of molecules, we want to cut exactly on the carbon heteroatom bond. Remember something that we have seen from the formation of amines point of view. So we know actually that this reaction is not the one that you would like to do in the lab. I hope you remember that, otherwise we will see that again in class. As a typical tips for this kind of simple disconnection, just remember that whenever you see, normally, not always, but normally, you want to disconnect the carbon heteroatom bond. And usually it requires, is preferable, let's say, that the electrophilic part is on the carbon. Check always that there are no other problems involving any other functional groups in terms of forward synthesis. As usual, let's see everything with a typical example. Let's say that the target molecule is the captodiamine, which is a sedative and tranquilizer. This is how it looks like. So, where do we want to start? We have two different heteroatoms, a sulfur here and a nitrogen. What you normally want to do first is probably cutting the carbon sulfur bond here. So in synthesis, you can imagine you want to start making a thioether. This one can be disconnected further. And normally what you want to do is introducing this thiol group using, for instance, methods like the thiourea method. In this case, we will start from the retrosynthesis point of view from the chloride, which via FGI can be obtained by an alcohol, which again, with another FGI, we can imagine starting from a carbonyl here. The carbonyl, in terms of retrosynthesis, can be obtained by a simple Friedel-Crafts acylation. So we can have this final molecule, which can be further disconnected later on to start from the thiobenzene, and all the rest of the compounds that I highlighted in green are actually commercially available, or they are small enough that we don't want to disconnect them any further. Remember that the synthesis might be a little more complex than the retrosynthesis, and also in this case we will see that in class. I want you to start thinking about any possible methods to do that, and hopefully in class we will discuss further. Let's move now to the formation of cycles, in this case saturated, and then we'll see also some aromatic heterocycles. What we want to do is normally counting the number of carbons that we have in a molecule, and if we want to obtain, for instance, this 5-member ring with a nitrogen on it, we can start from this kind of linear molecule. So the linear molecule, as usual, remember that there is free rotation around these bonds. So what you want to do normally is to put the bonds so that you can see the formation of a cycle. In this case, we will have the nitrogen here, which is a good nucleophile. The carbon next to the chloride here is a good electrophile. So by simple loss of this chloride, we will have the formation of this 5-member ring. In this case, we need a base again to neutralize the final molecule. Remember, for the formation of the cycle, the rate of formation of any kind of other cycles that we have seen mainly in the second year. So whenever you have this kind of molecules that can form a cycle, we need to evaluate the rate of formation of any kind of cyclization. So if we give, for instance, rate 1 to the formation of the 4-member ring, which we know is one of the most difficult one, we will see that the easiest molecule that we can form are actually 5-member rings or 6-member rings. We can do reactions like this one, which is a normal SN2, but we can do also formation of 1,4, also known as Michael attack. So if we have the possibility to have a double bond here and a nucleophile, and we can form a cycle via Michael attack, we can do that. We can also form lactones or lactams like we have seen in the past. Also, we can do a double nucleophilic attack or a cycle addition, and we have seen many cycle additions. We will see a little more towards the end of this video. What we need to remember is always that in the case of the formation of cycles, we always need to look for symmetry. So for instance, we have this target molecule as a typical example. Where do we want to cut? We have a nitrogen here, which acts as a heteroatom. So we have two actually carbon-nitrogen bond. So what can you imagine is cutting them both at the same time. So in terms of synthesis, we can start from this alpha beta unsaturated ketone, and these ones can come actually from the condensation of 3 different molecules of acetone. Saturated heterocycles can be used as activating groups for carbonyls. So for instance, we can exploit the formation of enamines to activate these carbonyls. We can imagine having a ketone like that, like acetone, but actually works with whatever kind of carbonyls like aldehydes, and a secondary amine. This reaction, the reaction between the two, will form an enamine. The enamine is in resonance with this structure where we have this nitrogen here with the lone pair. The lone pair can actually go back to form a double bond carbon-nitrogen, and this double bond can be used as a nucleophile to attack any kind of electrophiles. Actually, the most reactive of this kind of electrophiles are probably compounds that contain allylic function, benzylic, or with alpha halogen next to the carbonyl. The main activators, so the main saturated heterocycles that we can use as activators are probably pyrrolidine, piperidine, or morpholine. Let's say why we want to use this kind of activation. Probably you remember from the lab, you can have on this kind of cyclohexanons two kind of products, the thermodynamic and the kinetic. We know that the thermodynamic normally is favored because it forms the double bond once it forms the enolate on the most substituted position. But let's say that we want to do specifically the compound with the R group in this position. Then we can use this morpholine. In this case, we can form the enamine, and the double bond here will go specifically in this position because the other one, like you can see here, is very hindered. And then once you are activated this compound, you can use this double bond as a nucleophile to attack the electrophile, forming the intermediate, and then by simple hydrolysis we can form the desired target molecule. Let's move now to the synthesis and uses in retrosynthesis of aromatic heterocycles instead. You might remember a lot of different syntheses of heterocycles from the second year, but probably from the retrosynthesis point of view, one of the most important one for us is the Pal-Noor synthesis. It's important because it uses a dicarbonyl, in this case a 1,4-dicarbonyl. We will see the uses of dicarbonyls, especially in the next few videos. But for the moment, we know that we can use this dicarbonyl because a nucleophile, something like a substituted aniline, the nitrogen of a substituted aniline, can actually cyclises using the chemistry of the dicarbonyl. In this case, we can obtain a 5-member ring, so a pyrrole. But we know that it also works for 6-member rings, so we can also do pyridines with this kind of method. Another thing that we need to keep into consideration when we use heteroaromatics is the reactivity towards electrophilic substitution or nucleophilic substitution. The pyrrole, for instance, we know that is very prone to electrophilic aromatic substitution. And the most activated positions are position number 2 first and then position number 3. But a big problem, typical problem on pyrroles is that we know there is also the possibility of polysubstitutions. So for instance, if you have a pyrrole on a large molecule in retrosynthesis, always keep in mind that you might need to use, for instance, lower temperatures to block the substitution and go just in one position. Furans and thiophene have the same kind of orientation as pyrrole in terms of positions, but they are far less reactive. The pyridines instead, if you remember from the second year again, pyridines are sites of nucleophilic aromatic substitution, and they are not good at all for electrophilic aromatic substitution. That means that with whatever nucleophile, we can actually substitute one of the hydrogen of the pyridine, normally at least preferentially in position number 2, and the typical nucleophiles that you might want to use are methoxy, amides, but you can also have a variety of others. If you have instead benzofuse rings, if you remember again from the lectures on heterocyclic chemistry from the second year, you just need to treat them as 2 separated rings. So for instance, if you want to do an electrophilic aromatic substitution on the quinoline, we know that it will go on the benzene part, because the pyridinic part is actually a site of a potential nucleophilic aromatic substitution instead. So if you have an electrophile, it will definitely go on the benzene ring part. If you have an indole instead, we know that we have 2 potential sites of electrophilic aromatic substitution, because the indole is very good for that. But instead of going to the benzene ring, most likely it will go to the pyrrolic part, because we know from the pyrrole itself that is very prone to electrophilic aromatic substitution. If you want to remember something else on the indole, just remember that instead of going in position number 2, which is typical of the pyrrole, because of different resonance structures, it actually prefers to go in the position number 3. Let's see now the use of aromatic heterocycles in retrosynthesis with a typical example. Let's say that we want to synthesize this target molecule. We have a furan with 2 different substituents. So from the retrosynthesis point of view, we can imagine cutting the carbon-oxygen bond in both sides, so basically in the same way as we did for the pyrrole. And also in this case, we have a 1,4 dicarbonyl relationship. So we will see the dicarbonyl relationship a little better in the next few videos. But for the moment, let's say that we can start from these synthetic equivalents. Let's see the forward synthesis now. Now, in the forward synthesis, I would like to focus on 2 different things. The first one is, instead of using this acetone, we can use this activating group. I would like you to start thinking about why do we need to activate this group. For the moment, let's say that we can use a base here. We can extract one of these alpha protons. We can create an anion, and then using the other synthetic equivalent, we can do an SN2 reaction, and we can form this open structure. Now we still have this ester group on top. So to perform the final molecule, we have to do hydrolysis of the ester group and then the carboxylation. This is the other thing that I would like you to think about for the in-class material. we have seen so many different ways to do the carboxylation of this kind of compounds. Can you remember some of them? Let's hope that we can discuss a little more in class. For the moment, let's say that we removed this ester group here and we can have our final open structure. So then by simple cyclization with an acid, we can obtain our target molecule. In the very last part of this video, I would like to talk a bit about other kind of cyclizations. Probably one of the most common one and one of the most useful in retrosynthesis, but also in lab, is the Diels-Solder. You might remember from the first part of this course, it's a reaction that occurs actually from a diene, which is this one, two conjugated double bonds, and a dienophile, which normally has an electrowithdrawing group conjugated to it. Via the movement of three arrows, we can form two new sigma bonds, and we move one of the double bonds. The diene can be part of an open chain, and remember that we can rotate the bonds until we get the right configuration that we can use for a Diels-Solder, but it could also be part already of a cyclic structure. The dienophile instead is crucial having an electrowithdrawing group conjugated. Otherwise, in terms of reactivity, it will not work very well. Let's see it from the retrosynthesis point of view. Let's say that we have this large molecule and we want to synthesize it. So, starting from the retrosynthesis point of view, you can immediately highlight that one of these double bonds can be site of a Diels-Solder reaction. So actually moving the three arrows, we can break these bonds, forming a sort of retro-Diels-Solder. Remember that it's a sort of retro-Diels-Solder because we are talking in retrosynthesis, but in natural synthesis is the formation of this cycle by movement of these three arrows. But for the moment, let's say that we can move the arrows so that we can isolate this diene, which can be very good for a Diels-Solder reaction, and the dienophile is also good because it has two electrowithdrawing groups, so we can imagine that this reaction will work very well. It's very useful working on this kind of Diels-Solder reactions because you will encounter quite a lot in different kind of retrosynthesis. The last example that I would like to discuss with you in today's video is the synthesis of beta-lactams by 2+2 cycloadditions. We know that beta-lactams are very useful in pharmaceutical chemistry, and we also know that this kind of cycle 4 cyclic compounds are very difficult to be made, both in terms of normal synthesis, but also in terms of cycloadditions. So, if we want to work from the retrosynthesis point of view, we can cut these two bonds in this direction, and in order to perform a good beta-lactam synthesis, one of the two starting reagents have to be highly activated. In this case, we can form this ketene, and we can do it in the presence of an imine. Instead, if you want to cut in this other direction, the highly activated species could be this isocyanate, and the other component might be this alkene. The good news is that they both work. So, from the synthesis point of view, we can imagine creating this ketene on the first part of this reaction by abstracting one of these alpha protons with a very mild base, something like triethylamine in this case. Then we can perform our thermal 2+2 cycloaddition to form our beta-lactam in a very high yield. If you want to start with the isocyanate instead, we can perform the reaction in the presence of another alkene. We can then produce our beta-lactam in high yield, and then of course we can do all the rest of the chemistry that the rest of the retrosynthesis might require. In summary for this video, we can say that we saw the synthesis and their uses in retrosynthesis of heteroatoms, especially focusing on the importance of the CX disconnections. The use of heteroatoms in cyclization, focusing both on the saturated heterocycles and the aromatic ones. And in the last part, we saw other useful cyclizations, especially focusing on the Diels-Solder and other kind of pericyclic reactions, for instance, the synthesis of beta-lactams. Thank you for watching.